Did you stand up last night?
No, no.
Sit up, right? Okay. I want to end the class. End the class for the semester. This is the last part, but don't be happy because this one maybe will take 2 or 3 weeks for the last part, because this is the most complicated. We need to go back to chapter 1 to use all the E and the H field for all the theory in chapter 1 about electronic and magnetic field. If you didn't catch up in chapter 1, then come back again. Okay? For the waveguide, you don't see 2 different conductors. There's only 1 conductor. Okay, they are the whole conductor of the waveguide. So your magnetic and electric field is propagating inside the metal holes. There's a metal hole. Okay, you exercise your wave at the beginning, and you propagate your wave to the end and propagate outside with the antenna, and you can broadcast your signal to all other your personal your cell phones. You can communicate with each other because you have waveguide to make an antenna. Understand? That's a huge one. Waveguide has an advantage, like it is a heavy, huge structure. Okay, waveguide is huge. The waveguide, it covered all the energy inside. So, not like the microstrip line, you have wave leak outside in the air. All the energy is covered, so the loss is very small on the waveguide. You can propagate your energy inside waveguide. I had an opportunity after I graduated. I worked in Sendai, the company, the UMT. Okay, they are making a waveguide. So I think I have some practical experience about waveguide. What can they do? But so for this class, we have just only very simple cases. But I can give you some my point of view about the practical as an engineer, as a micro engineer in the company making waveguide circuit. Okay. Okay. So what does the waveguide looks like? In your textbook, I think you have some photos about waveguide. I don't think you can understand, especially it is only gray and black and white, right? It's not beautiful. You can see that there are some holes, and they have different. They have like a band. This is a coupler. And this, I think this is the most simple one, but except it is a bending. It is owning a transmission line, using waveguide as a transmission line, but it's bending. It's a bent waveguide. Okay. And I copied some. I give you some photos. Actually, those are the adapter. This is not I design. I copied a photo from internet. but I did have some experience to design the adapter when I was in the company. They are all very similar circuit. It is an adapter. You can think like a transition between the coaxial cable to waveguide. Waveguide is just a hole, a rectangular hole, a metal hole. You need to something to transfer your coaxial cable to your rectangular waveguide. You will need these adapters. Like most of you know the adapter to transfer the 100 and 110 volt to I think it's 2.1 volt to your cell phone. 2.1? 5 volt? Okay. The ampere current is 2.1 or 1 ampere, right? You transfer the voltage and the current from the 110 volt to your cell phone. The name of that one, the circuit is adapter. This one is also adapter. Adapter means you try to change some interface to another interface. Okay, this is a waveguide adapter from coaxial to waveguide. Okay, and this is also an example of how we design an adapter. I use HFSS to draw the 3D model to design the coaxial cable to the waveguide adapter. This was the project of my previous students and also Professor Chen's students. We designed this one for undergraduate student. This is a project, 专题的题目. Okay? Yeah. You think that's hard? No, it's not hard. Once this is your title, your topic, and you will be failed if you cannot finish. You will finish it. You will do that. That's what we did in the project, undergraduate project. That's what we did. We have some results, and actually we finished the project of the adapter with another company. Have you ever heard the Huangliang, the company of Huangliang? Some of them, they bought some cable, coaxial cable, and they are trying to buy more connectors. I think Xuanyi, they are trying to buy the connector from the Huangliang company. We used to have the project with Huangliang. We make the adapters up to 90 gigahertz, and we did 90 gigahertz. And we did that before, and I have that sample. I think some of you, we saw that before, right? You don't understand? Okay, maybe you didn't pay attention. Okay, this is also adapter, changing from coaxial cable, adapting from coaxial cable to your waveguide. And sometimes we will have a coaxial port to the waveguide port, and you have the matching. Sorry, I didn't change this one. This is a matching structure. We do some design, the geometry design inside that, and you have the tuning screw to tune that, because it's not 100% your measurement and your fabrication and simulation result. Sometimes it's not matched to each other. So the best design is your design always have some tuning technique you can change after you make it. And this is the table of the standard rectangular waveguide. This is important. I will ask you in the final. In the final, it is important, one of the important part. So let's look at the frequency first. For different frequency you used, you will have different standard of the waveguide. For different geometry of the waveguide, they are using for specific frequency. If your waveguide is using for the fundamental mode again. Yeah, we will talk about a lot about the mode. Fundamental mode, we will talk about that later. Okay? If that is for the fundamental mode, you will have two kind of frequency. Look at this is the first color frequency. This is the second color frequency. Okay, let's look at maybe find out some example. Okay, let's use the C band. You can call C band, the waveguide of C band, you can call it WR137. You can call it WR137. Why? Because the geometry of the waveguide, you have the longer length A and the shorter, the height B. Okay? The dimension of A is 1.372 inch. How to say that in inch? You know inch? 英寸. Okay, so this is from Europe, not America. Okay, not SI, it's used as inch. So 1.372 inch, they call that WR137. Okay? The B is usually half of A. You can see the table. It's similar to half, right? Not exactly half, but maybe half was a little bit different. Okay. I think it's half point something. Can use this one. 2.25. Okay, they have some ratio, but they are not in constant. They are not a constant. You can see that B is always smaller than A and close to 2. The ratio is about 2, but they are not the same in the same ratio. Okay, those are the standard. You just copy. Don't need to think about the reason why. The standard. There is a standard for any other in the world. When you talk about WR137, you know the dimension A and B. Okay? Just remember they are in inch. For calculation, you need to transfer the inch back to millimeter. 25.4 or something. Okay? You need to calculate back to millimeter. If I give you, I asked you about WR90, you need to use this table, calculate to the dimension in one. Okay? You can see that for A in inch, 1.37, so WR137. 1.122, so WR112, right? 0.900, WR90. Did you see the rule of these two? This one. Okay? There's a reason. This is the only thing I know about YA, and B is also like a half, around half of A. Okay? According to this dimension, we will calculate the first color frequency and the second color frequency. Okay? How to calculate this? Is we are going to learn, and I will going to ask you in the final exam. This is question, and this for this and this is you will be asked in the final. Those are a lot of equations, and you need to give me the answer. Okay? You can always come back to this table to check your answer is correct or not. Because the answer, right? Hong-Hao, right? Remember that? You forgot? Okay. So, how about this line? Once you calculate the first color frequency and second color frequency, you will know the range for your waveguide usage. See, the first is 4.3, the second is 8.6. So they use this waveguide to propagate 5.85 to 8.2, and they keep some emergent. You don't use that if maybe your something will shift, right? So you will have some safe boundary. So you can check all the numbers. When you use this one, they are in the middle of these two numbers. This is a final exam. For calculate this one and this one, then you will know why, and you will understand about all the mode. Okay, all the mode. We will ask a lot of mode. Okay. For the waveguide, it's more complicated, not like coaxial cable, not like microstrip die. Maybe you think microstrip die is a little bit complicated, but the only thing you need to understand is you just change epsilon R to epsilon E. That's it. And others is just copy the equation. That's not a big deal. But for the waveguide, it is more complicated. We need to start from a very beginning about our the definition of electric and the magnetic field. We always use electric field, right? Okay. So, what is the general definition of our electric field in the coordinate of x, y, z? The total electric field, maybe I write down total, to remind us this is a total electric field, okay? Equals to, you guys should remember, Ex plus Ey plus remember? Remember? Okay, let me ask. Some students haven't get a point yet. 钟品俊 are you with us or no? You want to try? EF equals to, can bring anything you want to the answer. It will be a very long derivation for the two color frequencies. But I will try my best to keep you understand and keep you online, okay? What did you miss? What did you miss? I think I emphasized this not first time, right? Did you guys do this a lot of time, right? But you missed something. Can anyone help him? Vector. Very good. Is that true?
Unit vector. Where is your direction?
So you got those at the very, very beginning when I talk about the vector. You don't know what's the difference. You don't know which one to put, right? You don't know, you just copy the answer. You don't know the reason. Okay, thank you. Maybe another student can help. Cai Xinjun, come to revise this answer. Give me a correct answer. Okay, maybe I can do some help. Come here. How many times? I have a quiz, I have a midterm exam. I'm told in class how many times I've talked about this. I think at least 2 quizzes, right? And the midterm, and in class, again and again, I think this is more than the 5th time. The same thing. And you don't know yet, still you still know, you don't know either, right? What is the answer? Okay, you don't know, just can. I don't know what happened to us. Okay, got a right answer. Give you a point. So, do you know why? Scalar function equals to a scalar function. Vector function equals to a vector function. If you don't have the unit vector, it's a scalar. same thing. Good. Okay. For this one, we discussed before. And yes. Okay, Zhang Zuan. So what is this equation? Is that a special case or a general case? What does that mean for this equation? Huh? High harmonic. This is what I want to ask. What if I see K, or maybe I use the beta here. Let me change K to beta. What does this mean? Okay. What does that mean? This wave is propagated in what material? I want a quick answer, just a word. What kind of the material? If I use beta, yes. If you see beta only, there is no alpha. You don't use the gamma. It is lossless, right? Okay. Cai Weixiang, you have an answer. The right answer. Weixiang. What is this? If EX only have this part, what is this? What's this? Can you answer? No? You don't know? Okay. Anyone? No. Actually, it's too easy question. What's this? Okay. Only the forwarding wave, right? A positive direction to the positive z. The wave is propagating in the positive z direction, but this field is pointing to positive x direction. The wave is propagating in z direction, but the E field is in the x direction. Okay, go back to this is the very beginning about this one. Okay. Now we are talking about general lossless and the wave propagating in positive z direction. What is the general formation of your E field if your E field is propagating in the lossless material only in positive z direction? Your z total will equal to because I refer to only x direction, so I write down x for this case, okay? Just change the name. So it is E plus x exponential minus j beta z x, okay, for this term, plus Zhong Tinjun, come here for EY. I give you another opportunity. This is EX, right? You write down EX, right? How about EY? of your face looks like that? Too hard? Oh, now you it looks like it.
我在想那个方向会不会有？
Good. Correct. Okay. Then you can get a point. Focus, everyone. Now is the most important part here. Is that possible? Your direction of propagating is the same as your direction of E field. For X and Y, you don't have a problem, right? You just shoot.
Yeah.
How about Z?
Different.
Easy is the direction you're propagating, right? But when we study in chapter 1, they must be perpendicular to each other. P, E, and H, they should be perpendicular, right? But here is a problem here. Right? Huge problem not only to you and the ancient scientists. They also got a problem. What happened here? This is a huge problem, right? This problem is related to waveguide. If your X, Y, Z must be your E field, remember Poynting vector, right? If U, E, and H, they are perpendicular to each other to your propagational direction. You don't have this part, right? Right? But, it's a but. In waveguide, we do have this part. That's the key. You talk about coaxial cable or maybe strip line, those are TM mode. It's easy. We don't talk about maybe we don't talk about micro strip line. It's a quasi TM. If you are talking about TM wave, you always use this one. Always be true. Your E and H, they are perpendicular to each other, and your propagation wave P is also perpendicular to E and perpendicular to H. Okay. But something is wrong in waveguide. They have this. Okay? If you don't know this, how can I explain this? You need to understand this one, then I can explain you. So everything is a logic process of explanation. You need to understand from very beginning of the wave, what happened there, then I can explain you here. And you will find out the problem here. Okay? So, what can we do here? At the beginning, we don't do anything. I put a question mark. But your wave is still propagating in the Z direction, right? So, let me just write down something we don't know and we try to solve next week, okay? I just write down, maybe I use a different notation. This is a function, a new notation. This is not explanation, this is a new function of z, which is also a function of xy. Okay? Multiply, because everyone has this part, it is propagating in the z direction. So I take this out as well. Multiply z. Who is this? I don't know. We don't solve this week. Okay? We don't solve that this week. I just put an equation, a black box here. We don't do anything about that. But I write down the formation. Looks very similar to x and y. Okay? This one, I do some combination. I combine this and this and this and this together to have a new vector. Remember this is a vector, right? So I will put in E. Okay, I write down equation, the definition here. Vector E, it is a function of x and y equals to, this is a definition, equals to EX plus and x, the unit vector is plus EY plus y. Okay? I just combine it. I name it. This is a new function. So this one can become E O X Y plus E Z X Y. This is a scalar function. Multiply Z become a vector, and all of them multiply exponential minus J beta Z. I try to take the exponential part outside everything, and I have a new vector unknown and the new scalar unknown here. Okay? Can anyone understand? Everyone understand what I'm to do here? I try to change the general equation under some assumption at the beginning. What we assume? First, it is lossless. Okay? Second, owing to the positive z direction. You don't have the negative minus z part. We have only this part. We have only this one, right? Only positive. This is negative, right? Okay. And then this is general E for all the component of x and y and z. Okay? If you don't understand, I don't know if I forgot, is that from my derivation or the textbook? I forgot. maybe he didn't explain too much, but he has a result very quickly about that. Oh, this is a general form of E field. Maybe you can check your textbook, but I explained very well. And then we will stop here. Try not to forget this one. Next week, at the beginning of next week, we will start from here. This is a very beginning summation. Remember, we will have a derivation from here to here for 3 weeks. Don't forget everything and you will miss, you got lost, okay? This is a just start. I give you a general form. And you use this one to derive. Okay, this is a line. Don't. Hope you can continue to be continued, because next week you come back, maybe you will forget or something. Okay, if you cannot get, you still don't get it, you can follow my derivation of the PowerPoint. I'm doing the same thing. The same, right? Totally the same. See? And the details, I write it down. You can go to read the PowerPoint to understand why those less if you are getting along the everything. I think that basically the same. You can you have Dropbox, right? The link of Dropbox you can download. Okay. So if you can keep the memory of this for next week, we can start from these 3 equations, for E field and H field. Okay, that's good. That's the end of the class. Just